All right, we're going live now. Okay, we're now live. Welcome everybody to today's IQS quantum discussion. Our guest today is Sabine Hossenfelder, who is currently at the Institute for Advanced Study. I'm getting echo on my speaker. I have to turn the volume off on this. I seem to have the YouTube video playing at the same time that I was talking, so that wasn't a good idea. Anyway, our guest today is Sabine Hossenfelder from Frankfurt Institute of Advanced Study. She's very well known for her work on fundamental physics, including physics beyond the standard model, quantum gravity, and recently she has been working some of the time on quantum foundations. She's also a very well-known science communicator. She is author of the book Lost in Math, which you can't see because my camera is my virtual background, but there you go. She has a blog, Back Reaction, and has written for many scientific publications, and also has recently been doing scientific explanation videos on YouTube. So you should check out her YouTube channel as well. So welcome, Sabine.
Hi, Matt. Good to see you.
Yes. So I want to talk today a lot about quantum foundations. I mean, that's what these discussions are about. So I had a list of topics that I wanted to talk to you about. And then you added a question, which is why you wanted to talk about why you're interested in quantum foundations, which I hadn't thought of asking you. And it's not something that I ask people regularly because to my mind, it's always, well, the question is for other people, why aren't you interested in quantum foundations, right? Here we have a subject where, you know, at least according to the popular accounts, we need multiple universes. We know there's faster than light influences, you know, things aren't real until you look. Why wouldn't you be interested in that is the question that I normally think of. But then that's my area of research. So maybe you want to tell us a bit about why you're interested in quantum foundations and why you've recently been writing about that more often.
So I actually think what I proposed in my email was that we talk a little bit about why it matters, not so much about my own interest, but those two things are, of course, correlated, right? I mean, I'm interested in it because I think it matters. But the question is, why does it matter? I mean, you can reasonably take the point of view that who really cares, like what those people are talking about with their interpretation of quantum mechanics. And I think my take on this is that it matters because if you look at what's driving all this progress in our society, like the computer that you sit in front of now, and all the progress that we see in, say, medicine, or chemistry and so on and so forth, what does it go back to? Well, it goes back to imaging technology, computers, and what does that go back to? Well, it goes back to quantum mechanics. So I would say that pretty much all this progress, which we've seen in the past century in our society, eventually goes back to progress in the foundations of physics. And I know there are a lot of people who, you know, think that physicists are a little bit arrogant for making statements like this, but to me, it's just a fact. And I think that the foundations of quantum mechanics have some severe shortcomings. And thinking about it matters because it can lead to great technological progress. And I just think we're not done with this foundational work.
Right. So I do also want to ask you about whether you think there's a strong relationship to your other interests. I mean, it certainly seems that for a lot of people in quantum gravity, quantum foundations is a bit of an attractor, right? So you have people who start their life wanting to sort out the problems of quantum gravity, and then they end up writing a lot about the foundations of quantum mechanics. I'm thinking, you know, Lee Smolin, Raphael Sorkin, a lot of people, even Lubos Motyl is now writing a lot of blog posts about quantum mechanics. I don't read them, but it is a fact. So do you think that your interest in quantum gravity have led you towards this area, or do you see it as a separate interest?
Well, it's more that, so I've always been interested in both. I mean, you said that I've recently become interested in quantum foundations, but if you look at, my publication is, I've been writing papers about this for more than 10 years, and that wasn't the starting point. It's just that for a long time, I kind of felt like I can't really afford to spend a lot of time on it. Because it's a really tricky subject, and it's even more difficult to get money for it than for quantum gravity, and even that didn't properly work. So what I actually work on right now is dark matter, which has nothing to do with either quantum gravity nor quantum foundations. And so I think, the reason why a lot of people who work on quantum gravity end up doing something quantum foundation is that these two topics are just very, very closely related. And you can ask the question, like, why haven't we made any progress on quantizing gravity? And especially seeing that there are lots of very intelligent people who have tried to make it work for since the 1930s or something. And quite possibly the answer is because we haven't really properly understood quantization in the first place. And that naturally leads you to quantum foundations. Okay.
Yeah. So I think we're probably going to have some agreements on our disagreements. It's very early in California, to my mind, quantum foundations in physics is something that you need to talk about in the afternoon. I normally do my administrative work in the morning, so having a physics discussion at 8:30 in the AM. I know it's the evening time for you, but this is early for a physics discussion for me. So I apologize if I make any mistakes. But I think we're going to have some disagreements over some topics in quantum foundations. So maybe in a minute we should get into that. In particular, I want to talk to you about the whole issue of fine-tuning. So in the book that you wrote, I guess the main topic is about arguments to do with fine-tuning and naturalness and things like that in fundamental physics, not in quantum foundations, but more in high energy physics and quantum gravity and areas like that. But sort of more recently, there's a sort of paradigm of thinking about the foundations of quantum mechanics, which involves fine-tuning. I would say it's not all that widespread, but I'm one of the people who've looked at things that way, Rob Speckens, etc. So given that you're, in the book, you are quite scathing of the arguments to do with fine-tuning, maybe we can talk about it specifically in the context of quantum mechanics, because, in particular, a lot of people would say that superdeterminism, which is an idea that you have been associated with recently, is superdeterministic theories are fine-tuned. So let's just talk about the concept of fine-tuning as a whole. I think we need to sort of start by defining it, and people might have slightly different definitions. So I want to see if you agree with the way I tend to think about it. So the idea is just basically, look, you have a theory and there are some parameters, and or maybe you don't necessarily have a theory, but you have at least a space of possible theories, and there are some parameters defining it, and you find that you can only reproduce the world that we see. There's some very, very special choices of parameters, and those choices of parameters have no explanation from within the theory. It's just like, look, you have to pick the specific values of the parameters, and then everything works. But they seem to require explanation. So there's a few different ways of talking about this in quantum foundations, but the sort of canonical example, and I always end up harping on about Bell's theorem, but so here we go again. But the canonical example is that, if you have a theory with non-locality in it, a theory like the Broglie-Bohm theory, for instance, where you have a preferred reference frame and you have influences which act instantaneously in that reference frame. Okay, so there is a clear violation of special relativity going on in the theory. Yet at the operational level, when you look at the predictions of the theory, the predictions, you can't use that non-local influence to signal, and indeed you can't see the preferred reference frame from the operational predictions. So the idea is that, if the parameters of the theory had been chosen slightly differently, then you would see explicit signaling. And it seems like there's no explanation for that, right? So this is the sort of typical narrative of fine-tuning that you find in quantum foundations. So I wanted to sort of start by getting your opinion on, well, that, and also the issue in general of fine-tuning in physical theories.
Yeah, so I have several problems with this definition which you put forward, and it hangs on words like you have to make a special choice, or there's something that seems to require an explanation, and those are terribly vague phrases. And also, what you just said, like slightly differently, you chose something slightly differently. How do you even know that you could choose anything? And that, in my mind, makes this entire criterion entirely useless. There are good criteria for fine-tuning, and those come back to the question of what can you even do with a theory? Like if you have a theory in which you have to precisely choose a large number of parameters to explain your data, you would correctly say, well, that theory is completely useless because I can't make any prediction with it. And I would agree, that's a huge problem. And I think this is what people had in mind originally when they were criticizing superdeterminism. Like this whole idea, okay, it would blow up science and all that kind of stuff. But now it's become more a criticism of the type of theory, like mathematically, what properties does it have? And in my mind, what properties the theory has doesn't really matter as long as it makes good predictions. And that's certainly the case for superdeterminism. And I mean, take, for example, what you just said about Bohmian mechanics. I mean, we all know that there is a simple criterion to get rid of this problem. And this is why, in my mind, I would say the theory is not fine-tuned, exactly because you have a simple criteria and an assumption that you can make to get rid of it.
Yeah, I mean, I guess so. So my approach into this subject is a little bit different, right? So if you look at the history of quantum foundations, going back to say the 1950s when Bohm and Everett and people like that were working. At that time, there was an awful struggle to get anybody to recognize that there were any problems at all, right? And coming out of that whole era and the decades after it, there came a sort of to prominence the idea that the main goal of working quantum foundations, perhaps the only goal, is to solve the measurement problem, right? So we have the standard interpretation of quantum mechanics has a measurement problem, you have to solve it. And that was the main goal. In modern times, we have solutions, right? So we have, to some degree, all of the interpretations of quantum mechanics that are worth their salt do solve the measurement problem in one way or another. We can disagree about the degree to which those solutions are good or not, but most people agree that there are solutions to that. But still, we're not satisfied with if the goal was to solve the measurement problem and that's it, then we should be done, right? Because we have several potential solutions. But a lot of people, including myself, feel that none of these interpretations of quantum mechanics really smell right somehow. There's still something wrong. And, the fine-tuning narrative in quantum foundations, to my mind, is supposed to attempt to make it more precise exactly what we mean. It's one thing to say, for example, well, I don't like non-locality, that's why I don't like de Broglie theory, right? But then, nature doesn't really care what you like, maybe it's right, okay? So the question is, is there something wrong with these interpretations that we have as it stands? And so my goal with trying to articulate these sort of fine-tuning arguments in quantum foundations was to sort of make precise there's a common feature that these interpretations have. Now, I will agree with you on several things. So one is, you can't specify a notion of fine-tuning unless you have a space in which to specify it, right? So, you could say any theory is fine-tuned if you say, okay, the space of possible theories I'm considering is every logically possible mathematical structure, because then in order to specify the objects of your theory, you need, a very, very large number of parameters to pin down, large number of axioms, which, if your space is everything that's logically possible, is a lot. So you sort of need to have reasons for varying things, right? So it's, it's you can talk about fine-tuning within a class of theories, within some space of theories. And if that's not precisely defined, you can't really talk about the notion. But I think, well, okay, I mean, maybe we can talk about the de Broglie example a bit more, right? So just to say that there is a fine-tuning, I agree with you, isn't an especially big problem. So if you identify something like that, in the case of the de Broglie theory, for instance, the way this works is that you will reproduce the quantum predictions if the distribution of particle positions at, say, the beginning of time obeys a certain rule. Okay, so if it obeyed the quantum predictions at the beginning of time, then it will obey the quantum predictions later. Okay, so two ways of explaining that is, one way is to just say, well, it just was the case at the beginning of time that this was the distribution of particle positions. And another way is to try and say, and this is the approach that Anthony Valentini likes to take, for instance, is to say, well, maybe it wasn't. Let's look at what happens if you have another distribution of particle positions and try to show that there's a kind of equilibration process that the distribution will be driven into the quantum distribution over time. So I would agree with you, I will at least agree with you that the second one is an explanation for why we see this apparent fine-tuning. Okay, and so once something is explained like that, I mean, it's a matter of terminology. You can either say, well, it's not fine-tuned, or you can say it's fine-tuned, but there's an explanation for the fine-tuning. Either way is okay. But I would argue that I don't accept that second explanation until I see the effects of the initial non-equilibrium distribution. It makes a prediction. The prediction is that sometime in the early universe there would have been explicit signaling, for instance, explicit non-local signaling. And until I see that in the data, I don't know, cosmological data or whatever, then I'm not convinced that that's a good explanation of the apparent fine-tuning. So, I mean, would you agree with that? That if we have this kind of explanation, that we should verify it by seeing that the fine-tuning basically didn't hold at some point?
So my biggest problem with what you just said is the question, like, why should I worry about a theory being fine-tuned according to a definition that someone made up? So if you say that Bohmian mechanics with the equilibrium hypothesis is fine-tuned according to some criteria. And I'm like, so what? Okay. And yeah, Valentini creates a problem by throwing out this assumption. And then he makes up some complicated story about the initial conditions and dynamical laws and so on and so forth. And then you can try to, now you have a different theory, right? I mean, this is no longer the original version of Bohmian mechanics with the equilibrium hypothesis. And then you can say, well, it makes some predictions and we can look for that. And to my best knowledge, we haven't found it. And so I don't have a big problem with that, but I also don't really know what we learned from it, other than it was unnecessary to throw out the equilibrium hypothesis to begin with. And so, I mean, you can do this as you correctly said. You can do the same thing for any kind of theory. Throw out some assumption, like, I mean, Born's rule in normal quantum mechanics, or you can, I don't know, take the universe and throw out the assumption that the cosmological constant has a value that fits to what we observe. And then you can complain that there now is a large number of possibilities, most of which do not actually describe what we observe, and call that fine-tuning. And I'm like, this is complete rubbish, because we know what the assumption is to solve the problem. And for Bohmian mechanics, it's the equilibrium hypothesis, the quantum mechanics is Born's rule, and for the supposed multiverse, it's one particular value of the cosmological constant that fits to our observations.
Yeah. So, I mean, this is always and you know, this is definitely a problem with defining this kind of concept, which is that, you know, one possible answer is just always things are the way they are, right? The choice of theory and theory space is just what it is. You know, I would say, you know, I am not. I mean, let me be clear here. I'm not so gung ho about fine tuning explanations that I think that they're be all and end all of everything. I think, you know, what we're trying to do here is, and you know, I'm not convinced it's successful, but we're trying to sort of reveal structures which, at least, you know, historically in some examples have led to a way forward. So, you know, the comparison example, I guess the strongest comparison example is something like the equivalence principle, right? So in Newtonian gravity, you have two roles for the mass. You know, you have the inertial mass, which describes how difficult it is to get something to change its motion. And then you have the gravitational mass, which describes how strongly an object attracts another object. And both of those in Newtonian gravity have the exact same value. They're the exact same quantity, but there's no real explanation for that. And of course, there are other theories like electromagnetism where those two things come apart, right? And so in that case, it seems like, you know, you could consider a space of theories in which the gravitational and inertial masses are different. And you could sort of ask the question, well, why don't we see that? And of course, you know, most of us think that it was a tremendous success to, you know, for Einstein to come along and say, well, there's actually a reason these things have to be the same. It's, you know, it's because basically gravity is not a force and space-time is bent, and, you know, you end up with an explanation in which it's necessary that those two things have to be the same. And so, I mean, I wanted to get your comments on that example. I mean, do you think that there's something fundamentally different about that example than the things that we've been talking about? Or do you just think that it's a bad idea to think about that in terms of fine-tuning?
Well, I think you're just throwing together two different questions. Like, I mean, you seem to be saying that if you don't allow fine-tuning arguments, you're not allowed to ask for a better explanation for something. That's certainly not what I'm saying. I mean, so, I mean, look again at the example of the equilibrium hypothesis or Bohmian mechanics. So if we would find a better explanation for this, by which I mean something that's simpler in some sense, that would be great. You know, I'm certainly not against it. We haven't found something better so far. But I mean, if Valentini wants to try to find something better, fine with me. But the question, the other question that you originally raised was, if we look at something like superdeterminism, is it fine-tuned? So, those are, in my mind, just two different things. I mean, also, I made a note here. So you said something about there's always this answer that this may just be the way things are.
Yes.
And I think that's not true, because there are some cases where you have a theory that is actually truly fine-tuned, and it's a problem for the theory itself because it completely lacks explanatory power. Like, if, as I just said, if you have a situation where you have to specify so many parameters that you can't explain any data with it, that's an actual problem for the theory.
Well, that you can explain any data with it because you have a problem of overfitting, basically.
Exactly. That's basically what it is in my mind. You know, an actual fine-tuning problem is an overfitting, a theory that can fit anything.
Mm-hmm. Okay. I do want to move on to talk about superdeterminism in a minute. I mean, I would give, I mean, you know, maybe sort of to some degree a question of that there's a terminological question here, because, you know, maybe what I'm talking about shouldn't be called fine-tuning. I mean, it certainly seems like, to my mind, you know, what we're trying to build is sort of a narrative, particular narrative about the no-go theorems in quantum foundations in particular. So Bell's theorem, quotient-Specker, contextuality, the whole list. And you know, so it's come out, this notion of fine-tuning that I'm talking about has come out of sort of a generalization of those kind of ideas. And we do somehow tend to find that when you find a fine-tuning of this type, you also find, and, you know, and this is a practical, more of a practical thing, but you also find some kind of advantage in information processing, because you know, your classical simulation of that has to have a property which is related to this fine-tuning that you can exploit. So it seems like there is something useful to that notion. Whether it's something that we should be worrying about in the fundamentals of the subject, in the foundations of the subject, that's something that we can disagree on more. But I do want to move on to superdeterminism in particular, and, you know, we've mentioned it a few times, and I have to apologize because the light in my office is on a timer, and I would have to go over there to make it turn on again. So I think we'll just keep with the Halloween lighting. Anyway, I think, well, first of all, maybe we should clarify for our viewers what superdeterminism is. So do you want to start by you know, giving a brief discussion of what that means?
Yeah, so people tend to get very, very confused about what superdeterminism is, because I think the name is just totally undescriptive. You know, people always ask me, how can something possibly be more deterministic than being deterministic? Speaking of funny lights, so the sun is setting, which is the reason for this problem, but it will disappear in 1 or 2 minutes, so don't worry. Okay. So the answer is superdeterminism isn't any more deterministic than just vanilla normal determinism. And I have no idea who came up with the word or why, but I don't know anybody who actually works on it who likes the word, which is why we've tried to rename it, but that's a different story. So the defining property of superdeterminism is that it violates an assumption that's called statistical independence. And loosely speaking, this means that if you have an underlying theory with hidden variables that explains the observations we normally attribute to quantum mechanics, then those hidden variables have to be correlated with the detector settings. And there's a lot of confusion about what exactly that means. A lot of people seem to think that this is already non-local, which I kind of feel like Bell must find terribly insulting, like if he was still alive. because the only reason he was even considering superdeterminism is that if you want to restore locality, causality, and determinism, then the theory has to be superdeterministic. And now it was thrown out basically because of fine-tuning arguments and slightly different arguments from the ones that people are making now.
Yes.
But the reason, I believe, why people were originally discussing this problem to begin with was exactly because it's the way to restore locality, causality, and determinism.
Mm-hmm. I mean, so I want to. Okay, so there's a few things I want to bring up here. So one is sometimes people distinguish. In fact, often people distinguish different ways in which the statistical independence hypothesis can be violated, right? So I personally like to talk in terms of retrocausality. That's the type of theory that I have been considering. But people also, people talk about sometimes superdeterminism, retrocausality, and lack of free choice, perhaps, as three different options. Do you see those as distinct, or do you think it's basically all the same thing?
Yeah, I've noticed that the literature is like terribly inconsistent about the use of any of those words. Like, for example, some people have told me that superdeterminism is by definition fine-tuned. And I'm like, well, okay, if you think that's the definition, then there's nothing to show, right? If you're arguing that it's fine-tuned. So what are those people writing papers about? To which the answer is, well, those were different people who had a different definition. And so personally, I would say retrocausality is really a term that doesn't really make a lot of sense to me. So I stick with superdeterminism, and then I talk about future input dependence, which is a term that I've stolen from Ken Wharton, and I'm afraid he might not be entirely happy with the way that I actually use it. But I find it just more descriptive. It's like, so personally, I can't really make sense of the word retrocausality. What does it even mean? Like, I would say if you have something in the future that influences the past, then I would just call the thing in the past the cause of the thing in the future. So there's nothing retrocausal by definition. So which is why this term just doesn't make any sense to me. Then again, you would probably call the thing that I call future input dependence retrocausality.
Well, yeah, I mean, all of these things just depend, like, in order to talk about retrocausality, you have to have a theory of causality. And there are different theories of causality. So different, it's a huge area in philosophy, and different definitions are going to come up with different results as to what is true. I mean, I certainly, just to clarify, I certainly don't believe in anything like a fundamental notion of causality in physics. It seems like the laws of physics don't have to do with cause and effect. They have to do with, how things are correlated in space and time. And any notion of cause and effect is something that we put on top of it. But it can be useful to put those things on top of it and see what happens. But anyway, I don't want to spend a lot of time going into this. So I do want to talk about the question of whether superdeterminism is fine-tuned or not. Now, of course, when it comes to retrocausality, and you could say the same thing about superdeterminism, there's a question, so the fine-tuning argument would go something like this, right? And maybe you've heard other fine-tuning arguments, but let's talk about sort of my style fine-tuning argument for this. So there are these correlations. So the hidden variables contain information about the future measurement settings at an earlier time. In a complete, so if you were to be able to somehow view the complete hidden state, you would know the hidden variable, you would know the measurement settings in the future, what they're going to be in the future. And if you think that somebody is basically free to choose those measurement settings, then it seems like there would be a way to send a signal into the past. But we don't see signals into the past because you can't know full information about what the hidden variables are. They have to be hidden, right, in order to preserve. That's just the fact that we can't send signals into the past. So again, there's a question here, which I know that you're probably going to dismiss this argument in the same way as the other ones, but it's like, well, why are the parameters of the theory chosen in such a way as to just shield us from ever knowing this information? It seems like in an arbitrary theory that had this kind of effect in it, you would generically expect to be able to at least see a hint of that information prior to, a hint of the information about the future measurement settings prior to actually making the setting. So I don't know if that's what you would view as the fine-tuning argument that people give, but maybe you could comment on that briefly.
So first thing to say is that I have no idea what it means to send a signal into the past. As I just said, this terminology just doesn't make any sense to me. I would say if you send a signal into the past, that's the same as sending a signal from the past into the future. It's like just by definition. Now, I understand that there are some people, who work with these causal models and so on, who are using quite a different notion of causality. And indeed, the way that I've phrased it in some of my papers is that in superdeterminism, those two notions can conflict, which normally doesn't happen. Which is why you can have this weird dependence on a setting, which will only be chosen in the future. But of course, this setting, this is a deterministic theory. It was determined by, a much earlier state. It's just that, and we basically know this from quantum mechanics. If you use a particular combination of all those variables that define the initial state of the detector, then that greatly simplifies your theory. And in science, a simplification is always a bonus. And it's basically because you can use the detector setting in your theory instead of caring about all the details of the initial state of the detector that the theory is not fine-tuned.
This argument, maybe you can try and clarify that a bit. I'm not sure I followed the details of that.
So the way that I've come across the fine-tuning argument a great many times is that you would have to get the hidden variables to be just exactly right to fit to all possible initial states that would lead to the same detector setting, because the experimentalist could call their grandmother and ask what she had for lunch, and then choose the setting accordingly. And I'm saying this is all completely irrelevant. If you look at the actual model, you never need to know those details to actually make a prediction. The only thing you need in the model to make a prediction is the measurement setting at the time of measurement. And now you can say, well, but we don't actually know this, to which I would say that's entirely correct, but we always have this problem, also in normal quantum mechanics. We don't actually calculate the measurement setting from the initial state in the laboratory. What we do instead is we make a prediction for all possible measurement settings, and then we compare our prediction with the setting that we actually choose. And that's exactly the same thing you do in a superdeterministic theory as well.
So it's, to rephrase a bit, the measurement setting itself is like, and maybe this is using language that you wouldn't use, but it's effectively screens off all of the stuff that you might use to choose the measurement setting from the system itself, right? So it acts as a sort of screening off, and we do the same thing with in a more conventional way with preparations. When you talk about the preparation of a quantum state, you can just use the quantum state itself, and all of the details of the device that was used to prepare it are irrelevant. So, I mean, I would perhaps use that as an argument for retrocausality, but as we've discussed, it's these terms are a little bit unclear and interchangeable. We are getting a lot of questions in the chat room now, so I might bring in some of those at the moment. We will have a Q&A session at the end if there's other people. Somebody asked, I guess the first question was, somebody was asking about the Wheeler-Feynman theory. What about what happens in the Wheeler-Feynman theory? So I guess, would you call that theory retrocausal or superdeterministic or anything in this context?
Remind me, was that the one where you have only one particle that goes through the entire universe?
Yes, and then it switches backwards and forwards in time. And there's actually a couple of Wheeler-Feynman theories. So there's that theory. There's also, there was a version of electrodynamics that they proposed, which used a similar kind of effect. And I think that the goal was to eliminate fields. So instead you had influences propagating backwards and forwards in time. Yeah, but there's basically this idea.
So I've never thought about it. So now I have to think a lot on the snap of a finger. I guess I wouldn't call it retrocausal. I mean, you need some kind of consistency conditions. I mean, this is normally what it comes down to, right? And you can formulate them by using a constraint in the future. That doesn't mean that there's actually a cause propagating into the past.
Yeah, I mean, so there is basically a very common difficulty with this whole area is, the difference between mathematical formalism and reality, right? So every physical theory that we know has, at least half a dozen different mathematical formalisms. And some of them, if you take the picture of what those formalisms are saying sort of literally as a picture of what's going on in reality, they would tell you very different things. So, even if you look at classical mechanics and you look at Hamiltonian mechanics versus Lagrangian mechanics, Lagrangian mechanics seems to suggest that everything's sort of happening all at once in space-time, and there are, you typically do impose boundary conditions at the initial and final time, but you also don't have to do the physics that way. So when I think about,
it's even weirder if you use the principle of least action,
yes,
which also
exactly,
seems to rely on a boundary condition in the future. But then if you derive the Euler-Lagrange equations, you don't actually need it.
Yeah. So but that that's one of the reasons why we try to. So yeah, I mean, it's sort of clear that you can't prove anything about anything without assumptions, right? So you certainly can't look at a formalism and say, okay, that's causal, that's superdeterministic or whatever. What you can do is you can formulate assumptions about your physical theory, about the nature of reality, and prove, well, under this set of assumptions, you must have X, Y, and Z, right? But there will always be other options, right? So you can, for instance, decide that you want non-locality instead of superdeterminism, or you can even, I don't know if we want to go in this way, but you can sort of give up on at least on aspects of scientific realism, etc. So there are always options.
As long as you stick with interpretations of the same theory, I would agree with that. But if you actually modify the theory, that's an entirely different game.
Yeah, I mean, I'm not sure I really agree with that distinction. It's a distinction people often make, and it's actually one of those distinctions which is can be somewhat marginalizing for the interpretation of quantum mechanics. So, historically, people have wanted to separate off, the practical aspects of this theory, the stuff that we do to make predictions, from the interpretation, with the idea that, the interpretation is doesn't change the theory, and it just, it's just, well, there's different ways of talking about it. So, we can to some degree sort of take that whole thing and put it off to one side. But I don't think that's ever really been true. I mean, I don't think that there is a sharp defining line between interpretation and prediction, if you like, because I mean, certainly I don't think that there's any other area of physics where we've made that sharp distinction. And it seems to me that all of whether something like de Broglie-Bohm theory is an interpretation or an alternative theory really depends. I don't want to keep harping on like the Valentini stuff, but I wouldn't say that's a different theory from standard de Broglie-Bohm theory. In fact, Bohm himself considered non-equilibrium distributions back in the 1950s, so it's been there from the beginning. It's if you make a particular hypothesis, it agrees precisely with quantum mechanics. If you don't make that hypothesis, it doesn't. And it's kind of like, well, that hypothesis isn't there in other interpretations, right? So it gives you a different sense of the space of possible theories. And this is true with pretty much all interpretations, even many worlds, right? I mean, I don't necessarily want to spend a lot of time talking about many worlds with you, but even there, they have the idea that you can just take an equation like the Schrodinger equation, look at what the state does in time, and somehow read off of that a description of multiple branching universes. Well, if you believe that, then you should be able to say, well, if I had a different equation, not the Schrodinger equation, I could also apply the same techniques to it. So, if I then replace the Schrodinger equation with something else, I have a framework for talking about what would happen in that theory, which is different from what you would get in a different interpretation. So, certainly you would probably agree that when it comes to applying the theory in areas which it hasn't necessarily been applied yet, like quantum gravity, for instance, then there isn't necessarily a distinction. But I even think that there isn't a distinction at an even lower level than that. There are, I've seen arguments in papers on the archive which sort of turn on the way that you understand things in different interpretations and have consequences for experiments. So, back in the late 90s, there were arguments about the Zeno effect, the quantum Zeno effect, and whether it really happens. Well, this depends on what is a measurement, right? Because if you're saying the thing that you're doing counts as a measurement and it doesn't display the quantum Zeno effect, then you would say, oh, that effect is wrong, and people did. And so these things do turn on interpretational questions, I would say. But anyway, this is a bit of an aside. Sometimes I just go on random rants.
Yeah. So, if I may, I basically agree with what you said, but it wasn't really the point that I was trying to make. I agree that those interpretational questions are important exactly because we don't perfectly understand the theory, and there's very much, I think, more than a lot of people out there appreciate, that is still left to be worked out and that we don't properly understand. And if you have different interpretations of the same math, that can help you to push forward in one direction, which in the other interpretation just didn't get you anywhere. But what I was trying to say is that you said earlier that it's kind of a matter of perspective, which way you look at a theory, depending on what interpretation you use. And I was trying to say, well, if you have an entirely different theory, then those you would expect, if you call them different theories, that they have actually observable differences, and they are tangible, and you can actually tell them apart, which you can't with the interpretations. And now, we can debate back and forth what was the original version of Bohmian mechanics, but it's kind of like it's kind of doesn't really make a lot of sense to talk about it. I mean, the point is that, as you correctly said, if you don't have the equilibrium hypothesis, you can have deviations from quantum mechanics. So I would say that's not the same theory exactly for this reason. And it's the same with collapse models, right? They're physically different theories, like Penrose's theory. And it's the same with superdeterminism, at least, okay, depends on exactly what model you look at. I mean, there are some variants of superdeterministic models that are constructed to exactly reproduce quantum mechanics. Yeah.
Okay, well, we have about 10 minutes left of the main discussion before I'm going to go into Q&A, and there's quite a lot of people in the chat room already asking questions. I do want to then touch on something that you've written about recently, which is also close to my interest, which is about the question of the status of the quantum state. So you have a paper recently where you criticized this what's called the epistemic psiontic distinction. So just to give background, the idea is something like, when we talk about the wave function, the quantum state of a system, do we view that as a property of an individual quantum system, or are we viewing it something more like a state of knowledge, something more like what a probability distribution would be in classical physics? So obviously there's a whole literature on this topic, and it stemmed in part from work by Rob Speckens and Harrigan were the people who proposed what's now the conventional definition of this, at least in the context of realist interpretations. And then there's been a whole host of no-go theorems, including the Coetzee-Barrett-Rudolph theorem. So you have criticized this distinction. I don't know if you can sort of succinctly say at least what the main point of the argument, or at least one of the main arguments in the time that we have, in a way that would be accessible.
So, I mean, for starters, it's just a definition, and you can use this definition to formulate theorems and so on and so forth, and that's all fine. I have no issue with that. But of course, you also have to ask, like, what does this definition actually capture? And I don't think that the psi-epistemic ontic distinction that has become common in the literature, as you correctly say, is particularly useful to identify the kind of hidden variable theories that I believe Einstein was interested in. The kind of explanation where you would say, well, actually, the outcome of the measurement was predetermined by some kind of hidden variable that we can't measure. And for some choices of those hidden variables, the system goes to the one detector eigenstate, and for some other choice, it goes to the other. And the reason I ended up writing this paper is that I kind of naively, I never honestly thought about this very deeply. I naively had this idea that that's what's meant by psi-epistemic in this definition, and it turns out not to be the case. And this is why I wrote this paper with John T, in which we propose a new definition that we call a psi ensemble, which realizes this notion of the initial state can branch into several detector outcomes, loosely speaking. And that may be psi-ontic, or it may be psi-epistemic, depending on exactly how you define the wave function.
I mean, so this seems to address. So there's always been people like to talk about things in terms of the completeness of quantum mechanics, and of course, this terminology was introduced by Einstein himself. Quantum mechanics is incomplete, and so the question there is, if quantum mechanics is incomplete, what needs to be added to it? So that sort of way of looking at things seems to sort of presuppose that, if you say quantum mechanics is incomplete, then you're sort of saying quantum mechanics is, and then what's the addition, right? So to my mind, that way of thinking about things, which a lot of people have have adopted sort of almost presupposes the psiontic view. So to my mind, the goal of the psiontic versus psi-epistemic distinction has never, it's never been like the most traditional question in quantum foundations, which has always been like, can we solve the measurement problem? Can we get definite measurement outcomes? It's clear that you can do that either way, but there's a certain sort of structure of explanation which comes from a psi-epistemic theory, and that's what's been interesting to me. So, in all, to some degree, it all stems from the Speckens toy model, which uses these kind of ideas to explain, a whole host of quantum phenomena which you might have otherwise thought of as mysterious. So, the question isn't necessarily whether that whole framework is adequate for the whole of quantum mechanics, but it's about sort of, well, people make these arguments saying, for example, the double slit experiment is the biggest mystery in quantum mechanics, or, teleportation is very mysterious, or entanglement swapping, or these kind of things. But can we say whether that's really true? Like, what should we actually be focusing on in quantum foundations? So to my mind, the distinction was always sort of about that. And if you look at it outside of the context of, like, if you look at it outside of the context of something like Speckens toy theory and the type of explanations you have in that, then the whole thing is really sort of out of context, and you're talking about something else. So when people come and criticize the psiontic psi-epistemic distinction, which of course I'm quite invested in for various reasons, it often seems to me like, well, it's just missing the point of the whole debate. So, I'm not trying to necessarily criticize whatever definition you want to make, but I don't know that it's really a definition that replaces or is in any sense sort of equivalent to that. I don't know what you want to.
No, that wasn't really the point. Look, the thing is that you're like one of the 3 people on the planet who perfectly understands the psi-epistemic distinction and exactly what all the consequences are and so forth. But I have to deal with people who don't understand this, and who then don't understand how my model works.
Right.
Okay, and they think it's been ruled out by the PBR theorem, and I have to explain that no, that's not the case, because confusing as it sounds, according to the definitions used in this theory, the theory, even though it's an ensemble, is actually psiontic. And then they're like, well, that can't be. So you see, this is where the confusion comes from. And the paper's trying to address this confusion. Like, you said this as an aside in a sentence, like, it's kind of obvious that you can solve the measurement problem this way or the other way. But I think to the vast majority of people, that's not obvious at all.
That may be true. I mean, there's certainly. So Lydia Del Rio in the chat room says that there's 5 people that understand the distinction. I don't know who the other 2 are, so maybe she can tell. Okay, yeah. I mean, maybe we're coming to the end of our time here, so I don't want to. Let's not extend this debate too much further, because I want to get to questions. There is an awful lot that we could still talk about, because I think that we've, in an hour, sort of barely scratched the surface of some of these issues. But I want to open it up to questions from the chat room. So if you are in the chat room now and you have questions, please feel free to put them down. I'm going to go up the list a bit to some of the questions that came up earlier. So let's have a look. Okay. So we talked about so I'm going to try and find some of the good questions. So we have let's try and find some of them. Okay, this is a good one. So I expect I know your answer to this, given what you said already, but Tom Anderson asked, is superdeterminism compatible or the same thing as the block universe?
Well, they're certainly compatible. It doesn't really make a lot of sense to say they're the same thing because, I mean, superdeterminism is a property of a class of models.
I mean,
And
we could
the
instead
block
ask
universe just doesn't say anything about this property.
we could instead ask the question: do you need to adopt the block universe in order to make sense of what's going on in a superdeterministic theory? Do you think?
No, I don't think so. I mean, you could have, I don't know, I think you don't even need special relativity necessarily. It's just that, I mean, we know special relativity is fulfilled in reality. But I mean, if you just take this assumption of it's a violation of statistical independence, I don't see what it has to do with the block universe.
Now, this is a good question because I know that you've worked on this. So John 294 asks, with quantum computing pushing the research of quantum effects in ever-increasing detail, is it possible now to make experiments looking for superdeterministic effects?
Yes, that's an excellent question. So it's something that I've thought about a lot because that's why I got interested in this entire question to begin with. The brief answer is yes, I think you can do it with current technology, but I don't think quantum computers are the right way to do it because quantum computers, they're too big. There are too many components in them. You want to try and test it with a small and simple system where you don't have to worry about a lot of wiggling components and so on and so forth. And I've written a paper about this where I explain exactly what kind of experiment would do it.
And what kind of experiment what kind of experiment would do it?
Well, I mean, as I just said, superdeterminism in and by itself is a property of a class of models. But of course, experimentally, you can only test a particular model. And so if you want to make any predictions with superdeterminism, you have to pick a particular model. And there are a few out there. I have one. I have a toy model, and then I have a more sophisticated model. And there's Tim Palmer with his invariant set theory. There's Gerard Tooft, and then there are some more specific models that are not generally applicable. Let me put it this way. And the major difference between those is what are the hidden variables. Mm-hmm. And so at least in my mind, the obvious choice for the hidden variables are the exact degrees of freedom of the detector, just because we know they exist. And as I actually like the way that you phrased it, that you kind of have some kind of shielding in superdeterminism, where you only have to care about the measurement settings. And that gives you quantum mechanics exactly, if you assume that this shielding is perfect. But of course, a measurement apparatus is not just the detector setting. It has a lot of details to it. And so I've been arguing that the obvious thing to try is to use those exact details of the detector as the hidden variables. And if you do that, you can make statements about how often they should fluctuate, how likely they are to change. And you can use that to make predictions about the correlations of measurement outcomes. Roughly speaking, if you manage to make measurements in short enough sequence, you should see that they are actually more strongly correlated than in quantum mechanics. And so the kind of measurement that you want to make is, for example, a repeated measurement of non-commuting variables, which in quantum mechanics should be entirely uncorrelated. On the same state, preferably in a cold system, in a small system, in a short amount of time.
Okay. Okay, so some people are saying that I need to ask this question from Michael Podolsky. I suspect I know what your answer is, but so he's asked, how could superdeterminism explain a Bell-like experiment where the angles of the polarizers are determined by, for example, decimal digits of pi and square root of 2 on the opposite sides. For example, how could the hidden variables be correlated with the decimal digits of pi in this case?
Well, as I said earlier, it's completely irrelevant how you choose the measurement settings. That's just, it never enters the model. The only thing that enters the model is the measurement setting at the time of measurement.
Okay. There's a question here from Liam Hogan. What minority held theory is most likely to be proven or disproven in the next few years? And what is the evidence we're looking for to do that? That is a very general question.
Minority held theory. So is that the term?
That's the term used, yes. I guess it's like theories that are not viewed as likely by the majority of the physics community, but you think are promising.
Well, there are lots of people now trying to test collapse models like Penrose's and the other spontaneous collapse things. They're getting close to ruling out the relevant parameter range. And so, I guess those count as minority ideas. And yeah, I guess in the next 10 years or something, some of those will go out the window. But then, of course, you can make them more complicated. So it's the old problem.
Yes, I do expect. I'm not the world's biggest fan of collapse theories. I don't really like ranking things, but if I were to rank all the existing interpretations, they would be close to the bottom, and I expect they will be ruled out in my lifetime. I'm willing to make bets on that, by the way.
I would disagree that they're interpretations. I would say they're actually modifications. They're different theories.
Yeah, okay. Let's not go there again. So there's a question from Lily. How does the collapse of the wave function happen in relativistic quantum mechanics? On what time slice? I mean, I guess maybe you can spend a bit about time explaining how you think about the collapse of the wave function on the view of the superdeterministic theories you're interested in, and whether that's a relevant thing.
So, I mean, first of all, I believe that's exactly what Einstein worried about, right? You have a wave function that propagates into space, like, for example, a single electron that's nearing a screen. And the wave function tells you that it's distributed all over space, but the moment it hits the screen, it's at one particular point. How does this happen locally without being in conflict with special relativity? And in normal quantum mechanics, the answer is, well, this collapse isn't really a physical process. You just update the function, and there are no observable consequences of it. So it's kind of a pseudo problem. So this is the standard answer. And I think that this doesn't really give enough credit to Einstein's worries. And superdeterminism indeed solves this problem, because in superdeterminism, the wave function is an ensemble. That's why I proposed to call it a psi ensemble instead of being a psi epistemic. And the wave function really just describes something like the mean value of all the trajectories of those particles. And so they just individually go to one particular measurement outcome, and there's never any collapse. And now one can ask, of course, what defines the time slice of all those detections? And that's just the detector, right? I mean, the detector is a thing, and it defines a frame the same way you have this in condensed matter systems.
Yeah. Okay. So another question from Tom Anderson. I'm going to try and rephrase this slightly. So he's originally asked, many physical theories have been found to fail, for example, Newton's gravity. If QM is going to fail, where should one look? Can some form of superdeterminism be only approximately right? So, I mean, you've already talked about the kinds of effects that you might expect to look for in experimentally to test superdeterministic theories. But and there's sort of a bit of a deeper question here, which is like, where do you expect to find them? Because, you know, certainly the case that, you know, if you do an experiment with, you know, you would certainly expect things to break down more in regimes where quantum mechanics hasn't been rigorously tested yet, right? So if you're doing a quantum optics experiment on a tabletop and there were violations of quantum mechanics, unless they were extremely, extremely like tiny beyond experimental precision, you'd be very surprised. But you might expect that in regimes, for example, involving quantum gravity or whatever, that these effects would be larger. I mean, do you have any thoughts on where is the best place to look?
So again, it depends very strongly on what you think the right model is. So for example, Tooft, I think, believes that those hidden variables are really, really high energies. In which case, and we're talking about Planck energies or something like this, in which case, you know, you have the same problem with this as you have with string theory, because you're never going to see it. Now, in the case that I've been talking about, where it's actually just the degrees of freedom of the detector, is pretty straightforward, because we know the energy scales involved, and it does not require building big detectors. If you look, for example, at Tim's model, so this the invariant set theory idea, he has an upper bound on how many particles you can possibly entangle. And this is also something that you can look for. So it's a model-dependent answer, I'm afraid.
Yeah. I mean, it's another pet peeve of mine, which is that people propose alternative models of quantum mechanics, and then they go look for them in a tabletop optics experiment, find that they don't exist, and then say, well, we have very strong bounds on the existence of these models, but it's really not where you would expect to find any violations of quantum mechanics. So let's see, a couple of other questions. Okay, so we're going to harp on superdeterminism a bit. Carlos, who has a lot of names, I'm going to just say Carlos. What does Sabine think about the fact that one can always deny any experiment by saying that the way one chooses to measure the system under consideration is correlated with the system to be measured? So here's a worry about superdeterminism, that you know, perhaps it invalidates the scientific method, right? Because you go and investigate something, and you know, the fact that you're investigating it makes it behave differently than it would otherwise, right? So if we can't really say that we're investigating sort of the world as it is, does that undermine, you know, the scientific method? Is, I think, the worry here.
Well, no, it doesn't. So, I mean, if you have a theory that violates statistical independence, you can ask, does it explain our observations, yes or no? So, and that proceeds exactly the same way as the scientific method always does. I think what people are worried about, if I remember where this argument originally came from, is that you would have to accept violations of statistical independence for classical experiment. And the argument that people always bring up is something like cancer and tobacco or something, which you test in randomly drawn mice. And if you don't know that the mice were really randomly drawn and correlated with what you will go on to measure, and so on and so forth. And I think this is just, honestly, I think it's ridiculous, because we never observe quantum effects in macroscopic objects like cancer cells or mice, and so on and so forth. So those violations of statistical independence, which you need in Bell's theorem, are there to explain why we never see superpositions of detector eigenstates. Now, if you have a classical system like a mice or something, that's never going to happen anyway. So there aren't any violations of statistical independence. So the brief answer to the question is that no, I think there's nothing to worry about.
Yeah, I mean, so I think in any theory underlying quantum mechanics, you're always going to have an explanation for the emergence of classicality, and it's going to, in some sense, rely on some of the mathematics that we already have. But when you have a model in hand, you should be able to see how that happens. Obviously, I think it's a strong requirement on the consistency of any such model that you don't get those kind of effects happening on a sort of macroscopic classical level. Otherwise, it would sort of, just not be an empirically adequate theory. So that's basic, but it's sort of, I think we're at a sort of too early stage to be demanding too much of that now, because we don't really know what the right theory is along these kind of lines, whether it's superdeterminism or anything else like that. But once you do have like a full theory of that, obviously you have to ensure that it has a good classical limit where you don't get these kind of effects on a macroscopic level. Okay, let's see. I don't think that we have any more questions in the chat room. Let's make a last call for questions, if anybody else has anything that they want to ask. So while I wait for that, I do want to thank you very much, Sabine, for agreeing to talk to me today. It's been an interesting discussion. I think we could have gone on much longer and gotten deeper into some things, but maybe we'll talk again at some point in the future when we have done more work and understood all of quantum mechanics perfectly. Then we can talk again.
Well, thanks for the conversation. It's been very interesting.
Okay. Thanks very much, Sabine. And I do want to announce to everybody who's viewing, there will be another one of these in November. I'm still in the process of scheduling that, but it'll be the first time that I'm going to talk to some local Chapman colleagues. I'm going to talk to Kai Wagel and Kelvin McQueen. The theme for this semester's talks is basically all ways of getting around Bell's theorem that are sort of less on the less beaten path. So we're going to have a discussion in particular about many worlds type theories and the extent to which they are local or non-local. So that'll be coming up in November. And if you're on the email lists, then you can look out for that, or you can just look at the IQS website, quantum.chapman.edu, lists all our events. So thanks once again, Sabine, and bye for now. I'm going to